Hello everyone. Today I will talk about our recent proposal of developing a deuterated scintillator for detecting supernova neutrinos. This work was done in collaboration with Professor Basudev Dasgupta and Professor Vivek Datar. Let us begin by asking, what if, say tomorrow, there is a core collapse supernova in our galaxy? On the neutrino frontier, the water Cherenkov detector Super Kamiokande will observe several thousands of events, whereas scintillation detectors such as Borexino would see about 300 events. A large fraction of these events arise from inverse beta decay, which is only sensitive to the electron-antineutrinos through the charge current channel. In order to observe the muon and tau flavored neutrinos, we hope to rely on the elastic scattering of neutrinos on electrons and free protons in the target. However, the cross-section for electron scattering is relatively small, and the scintillation from proton is quenched. As a result, the event rate for these channels is quite low. So the question we are asking is, how can we reliably detect neutral current interactions of the neutrino? And by reliably, I mean clean and with large statistics. At this point, a small detour into history will be helpful. The heavy water Cherenkov experiment, SNOW, solved the solar neutrino problem when it observed the neutral current interactions of the neutrino through deuteron dissociation. The recoiling neutron thermalizes with the medium and was detected by a radiative capture on deuteron. The final state neutrino and the proton were not detectable. Learning from the success of SNOW, let us ask, what are the challenges that we need to overcome in building a similar detector today? First and foremost, heavy water is expensive and often unavailable. Moreover, SNOW had a large signal loss rate due to neutron capture efficiency. As it was a water Cherenkov detector, the energy threshold was high, around 5 MeV. As mentioned, the proton was missed altogether, and the detected neutron carried no spectral information as well. Here is where we find a unique opportunity. India is the largest manufacturer of heavy water. The neutron capture rate can be greatly enhanced by adding dopants such as gadolinium. And the issue of threshold and obtaining spectral information can be solved by having a scintillation detector. And thus, the idea of a deuterated scintillator for neutrino detection was born. We emphasize that India's heavy water board already has facilities that can manufacture deuterated compounds. Also, deuterated scintillators have been previously studied in literature for neutron detection, although in a small volume. We propose a kiloton-scale deuterated scintillator with added gadolinium and instrumented with PMTs that can study low-energy neutrinos. While the day job is to study solar and atmospheric neutrinos, in this talk, I will focus on the capabilities of DLS for detecting neutrinos from a galactic supernova. In a core collapse supernova, nearly 99% of the gravitational binding energy is released as neutrinos. We have used a provisional model for the fluence with two different choices for the average neutrino energies. We call them high and low fluence models. The details are in the table below. On the other hand, the flux of neutrinos for any flavor is negligible above 50 MeV, as is evident from the figure below. To calculate the event rates, we have used the framework of pi-less EFT for evaluating the cross sections, which is typically valid for low energies. The differential cross sections are tabulated and provided in the appendix of the paper as well as on my GitHub page. Let us now take a closer look at the interaction and detectables in the DLS. I will not talk about electrons and carbon because it is similar to any other ordinary scintillator. There are three major neutrino-deuteron interactions that will be discussed today and are listed along with their kinematic threshold in the table below. As you see, the final state is a three-body and has unique combination of leptons and hadrons. You cannot typically detect the outgoing neutrino in a kiloton-scale detector. The electron, positron, and proton are electrically charged and are detected by their scintillation signal. In principle, one can use pulse shape discrimination to distinguish between these signals. although with certain efficiency. The neutrons are slightly tricky, as they first thermalize in the medium, lose their initial kinetic energy, and eventually get captured, producing detectable gamma photons. We envision that the detector will have at least 0.1% concentration of gadolinium that makes the neutron capture efficiency almost 100%, as well as it takes care of certain secondary interactions. I would like to emphasize again that the three interaction channels have unique signatures in the detector. This is a crucial distinction from ordinary detectors, making a serious science case for DLS. Let us look at the main result of the paper. For a kiloton scale DLS with added gadolinium, we would observe 435 neutral current events and up to 170 events from the charge current interaction of the elusive electron-neutrino flavor and 110 events from nu-bar. This is for the case of high fluence, and the event rates are lower for the low fluence model. As expected, the neutral current event rates do not depend on the flavor conversion scenario, but the charge current event rates are sensitive to it. Since we obtain hundreds of detectable events, let us look at the spectrum of these events and see if we can uncover more. In the neutral current channel, the proton will generate a scintillation signal and the neutron gets captured on gadolinium. The gamma photons from the neutron capture do not carry the information of its initial kinetic energy, and getting any spectral information is hopeless. Reconstructing the incident neutrino spectrum using the scintillation from protons has two immediate challenges. First, the momentum transfer to the hadrons in the dissociation process is typically very small, as can be seen from the plot on the left. Moreover, due to photosaturation losses, also known as quenching, only a small fraction is converted into scintillation signal. As can be seen from the figure to the right, less than 10% of the energy is visible. Note that there is one-to-one correspondence between quenched and the unquenched energies. It means that at least in principle, quenching is invertible and not a serious threat to reconstruction. Let us now look at the event spectrum from protons. We find that a significant number of these are above the carbon-14 beta decay threshold at 200 keV. In the high fluence model, we find 84 out of the 435 protons are above threshold, and for the low fluence model, 50 out of 335 are above threshold. One must remember that these protons have an associated neutron capture signal that can be used to tag and get rid of certain backgrounds. Looking at the energy distribution of these events, one can reconstruct the incident neutrino spectrum as well. For the electron-neutrino charge current interaction, the scintillation from the electron is at a larger energies and has negligible quenching losses. Thus, it can be used to efficiently reconstruct the incident neutrino spectrum, although for the flavor electron-neutrino only. I would also like to mention that only liquid argon detectors such as DUNE will have reasonable sensitivity to this channel. The scintillation from protons will be a fraction of the electron signal. Moreover, these signals will overlap in time as well. It seems a priori that segregating these signals will be very tough, and we encourage detailed simulations that will reveal more about this. The event spectrum for nu-bar is similar. Even though the neutrons can be tagged there, this scintillation, this channel will be detected by Super Kamiokande with much better statistics. The details of this channel can be found in the paper. Let us take a moment to discuss the secondary interactions, which are very important. Without gadolinium, the final state neutron will undergo approximately 1000 scatterings before getting captured on either deuteron or carbon nucleus. We find that a significant number of recoiling neutrons have initial kinetic energy larger than the deuteron breakup threshold. For example, in the high fluence flavor equilibrium scenario, we see that nearly 70 neutrons could potentially break up the deuteron, whereas for low fluence no oscillation scenario, the number is 34. While a cascade seems extremely unlikely, this breakup can mimic the neutrino-induced dissociation. So either you statistically subtract these events during reconstruction or simply just add sufficient quantities of neutron capture dopants such as gadolinium or lithium. One last thing, what about the backgrounds? For supernova neutrinos, you get about 600 events in the 10-second window. In the relevant energy range, there is no other source of neutrinos that is as luminous. So backgrounds have been a non-issue so far. However, for the day job of the detector, which would be studying solar neutrinos, a detailed understanding of backgrounds is required. We look forward to simulations for providing estimates. Extreme radio purity, similar to what have been achieved for Borexino, may be required and poses an engineering challenge. Finally, the take-home message. A deuterated liquid scintillator is a promising candidate for detecting neutral current interactions of the neutrino. The additional particle in the final state, as compared to ordinary scintillators, will help in tagging and mitigating backgrounds. For a galactic supernova, a kiloton-scale DLS would observe more than 400 neutral current events, 170 elusive NUI events, and 108 events from the NUI bar channel. We note that the quenched scintillation of proton can, in principle, be used to reconstruct the spectrum of neutrinos through neutral current channel. Subtracting the NUI and NUI bar fluence inferred from their charge current interactions in the detector will reveal the spectrum of non-electron flavors. There are many challenges, both theoretical and experimental, in development of such a detector, but they are also opportunities for more research. Thank you.